Hello class, welcome to 5.3, the unit circle. In my last lecture, I had written it as 7.2, it should have been 5.2, just a quick note there. In unit circle, we will begin with sine and cosine values in the first quadrant, and then we will move on to finding more about the coordinates. So in sine and cosine, for the first quadrant, this is how we develop the idea. Now we know that if we were to draw a circle inside, in a grid, in an XY grid, and if I made sure that the circle was of radius 1, okay, we call that as the unit circle, okay. So unit circle has radius 1, right? And what this means is, if you looked at the equation of a circle, this is the equation of a circle with radius r and center 0, 0. Okay, so let's write that there. Center is 0, 0, and the radius is r. Now, with the radius is 1 for a unit circle, this becomes x squared plus y squared equals 1, because 1 squared is 1. So this red circle you see here has the equation x squared plus y squared equals 1. And if you were to choose any point, okay, any point P on the circle, the coordinate for that point would be x comma y, isn't it? Because that's your xy axis. And what we do here is we try to construct a right triangle. Okay, that could be better. A right triangle is when you can have a 90-degree angle in your triangle, right? And this triangle is formed by touching the point P of interest. Now we know that the radius is 1, so this should be 1, right? That line. And this being 90 degrees, you can see that this could be our angle of interest, theta. So with radius 1 and angle theta in this triangle, we are trying to see how we can measure this angle using x and y. Okay. So if you think of the sides that correspond to the x and the y, we can see that this bottom side of this triangle is your x, right? And this height here is your y. This is x and this is y. And that's how you get the x squared plus y squared equals 1. This is the equation of a circle, but this is also your Pythagorean theorem. Because Pythagorean theorem says c squared equals a squared plus b squared. And because it's a right triangle, we do have that measurement there, okay? So here we define, if theta is a real number, we're trying to do this in terms of, radians, so you can think of it as a real number. And a point x comma y on the unit circle corresponds to a central angle theta, right? Because that's where the angle is. It's made at the center of the circle, but inside the triangle. Then cosine theta is x and sine theta is y. Okay, it's defined that way. And we can see that because if you go back to the definition, okay, we said sine theta is opposite over hypotenuse, isn't it? And if you come back here, opposite for sine theta would be the side y, right? So the side is y over the hypotenuse. Hypotenuse here is 1 because this is a unit circle. So that is a 1, which implies if you solve for y is 1 times sine theta, which is basically sine theta. You can place the same argument here for cosine theta. Cosine theta is adjacent over hypotenuse. And if you come back to the unit circle with the triangle in it, adjacent side is x, right next to the angle theta. So that's going to be x over 1, which implies when you solve for x, x is 1 times cosine theta, which is cosine theta. So this definition is actually coming from this understanding. Okay? And if you also can see that if you replaced, let me also write that here, you have x squared plus y squared equals 1. And if you replaced your x with the cosine squared theta, and the y is sine squared theta, which is basically sine theta being squared, right? Sine theta times sine theta. We write it as sine squared theta with a 2 in between the sine and the theta. You don't put it outside, meaning you don't write, it's not the same as writing it like this with a square outside, because this would mean the theta is squared, okay? However, if you wanted to show the square outside, then remember to please bring the parentheses to show the square, and that way they will be equivalent. Okay. All right, so replacing x and y by cosine and sine respectively, you get cosine squared theta plus sine squared theta equals 1. This is one of the identities we'll be looking at later, Pythagorean identity, coming out of the Pythagorean theorem. And so you can see that they're also interconnected. Now, if your radius was r, not 1, if it's not a unit circle, but it's some radius r, then this formula would change to y equals r sine theta or x equals r cosine theta. We'll be talking about that shortly. For now, we're focusing on the unit circle. And so just to reiterate this idea, let me say, given p is, let's say, negative half comma root 3 over 2. Okay, if that point is given to you like this, what is cosine theta if theta is the central angle? Now, sometimes we use, t instead of theta. So feel free to be flexible about how the angle is denoted. The angle is usually denoted by theta, but we could use x, y, t, s, anything. Okay. The usual other go-to letter is t. If we want to keep it all in English alphabet, we do the t to avoid theta, which is Greek. All right, so from here, we know that p of x comma y is now given to be p of negative half comma root 3 over 2. So you know that your first coordinate is your x, and of course the second coordinate is your y. We also saw that, let me take you back up here. We just saw that x is cosine theta and y is sine theta. So you can come back and make that another connection, the other connection with the trig functions as sine theta. Okay. So now our question is, find cosine theta. So this implies cosine theta is directly equal to negative half. In fact, we can also say what sine theta is. Sine theta is root 3 over 2. So we answer the question there. Cosine theta is negative half. In fact, we can go beyond that question and even find tan theta, because tan theta is sine theta over cosine theta, which is root 3 over 2 divided by negative half, which is, upon simplification, would be like this, right? Flip the denominator. That gives us negative root 3 as your tan theta. And you can go on like this. Now, in fact, you can also interpret this on the right triangle. If this was theta, right? Cosine theta is opposite over hypotenuse. So opposite over hypotenuse. Hypotenuse, in this case, would be then 2, right? And opposite would be negative 1. And sine theta, I apologize, opposite, so cosine theta is adjacent over hypotenuse, so it's negative 1 here. And sine theta is opposite over hypotenuse, and that could be root 3 over 2, right? You could do it like that, but this would not mean that my unit circle, this would not mean a unit circle because the hypotenuse, which is the radius, would be 2. So in which case, if I want to keep this as 1, then I would keep the entire sine and the cosine as -½ and √3 over 2 with a radius of 1. So you can see that we have many views or interpretation to this information, but because we started with a unit circle, we want to always maintain our radius, which is the hypotenuse, to be 1. And then you have these details. So you can translate these details onto your triangle like this, instead of seeing it on a circle, or even seeing without a circle, just using the x and the y coordinates. You can see that x and the y coordinates can be interpreted as sides of a right triangle. So how do we know these values, or how do we know what these could be? So if you took a unit circle, okay, and if you were to draw these angles, I'm going to just do that quickly here. So let's say we had a unit circle like this with differing angles, okay? So this could be the 45-degree mark, okay? I didn't want to, technically I should be doing this as 45 degrees, right? I just don't want it to get too crowded, so I'm just going to write it out here. So let me just remove that. And this could be the 30-degree mark, and this could be the 60-degree mark. And then, of course, we have the 0 degrees here and 90 degrees here. And these will equivalently be written in terms of radians as well. We'll come to that. Now, these are called special angles just because we know a little more about them, and they're kind of easy and nice. But theta can be literally any angle. It could be 45.73 degrees, you know, something like that, or 39.82 degrees. So it can be anything. We're just looking at these good ones, special angles we call them, to see if we can represent the coordinates for these points on the unit circle. So our focus is what will be the coordinate for these ones. Okay. Now, if you look at 0, the coordinate for at that point on the blue circle will be 1, 0, because the unit, it's a unit circle, so the distance, this whole distance, when it reaches up to the circle, is 1, right? The whole radius is 1. And because it's the xy plane, it's 1, 0. Likewise, if you come to 90 degrees, the height is 1, so it becomes 0, 1. So those are easy for us to kind of detect. What about 30 degrees, 45 degrees, and 60 degrees? What would those coordinates be? Now, for that, we kind of understand this by drawing, you know, the right triangle. So let me show it for one of them. So if you see that with the 45-degree mark, I've drawn a right triangle, and we could use the idea of right triangles here to build the idea of, or to get the coordinates. Now, this is 90 degrees, so I'm going to kind of draw this outside, otherwise it's going to get cluttered. Right? So, excuse me. So if you have 45 degrees here, and this is a right triangle, 90 degrees, we know that the 3 angles of a triangle should add up to 180 degrees, exactly. So you already have 45 and 90 taken up, which means the other one must also be 45 degrees. This makes it an isosceles triangle. That means 2 sides are equal because there are 2 angles that are equal, right? So the opposite sides of these angles must be equal. So what happens is you have, we have the unit circle to be 1 here, right? So the unit circle has the radius 1, so the hypotenuse is 1. So we have no problem there. And so we have to understand that the other 2 sides, right? We don't know what these 2 sides could be. So let me call them as A and B, okay? Now, these are the 2 other sides of a right triangle. And I call them A and B because they are the other 2 legs of the triangle. However, being 45 degrees, both these angles, their opposite sides must measure the same distance, right? The same length, I mean, sorry, the same length. So in an isosceles triangle, that's one of the properties. Two angles are the same, therefore their corresponding opposite sides must be the same. So I'm going to call this B also as A because B and A are the same. So if I come here, x squared plus y squared equals 1. That is the equation of a unit circle where radius is 1. And your x and y are the sides actually, but in this case, they are a squared and a squared because x and y are both a. Okay. So that makes it 2a squared equals 1, a squared equals a half, and you're solving for a basically. So a is plus or minus the square root of half, but because we're looking at the first quadrant, this must be a positive 1 over root 2 or half with a square root. I'll just put it like this. I'm sorry, I did the same thing. So it's a positive 1 over root 2. Now we know that if it is positive square root of half, we can rewrite this as 1 over root 2. However, you don't leave a root 2 in the denominator. We have to rationalize the denominator. So you multiply up and down by root 2 to remove or eliminate the denominator containing the radical. So this in turn gives us square root of 2 over 2. And we have, well, the radical has moved to the numerator, which is not a problem. We have no problem if the radical moves to the numerator. We can't have the radical in the denominator. And therefore, we have rationalized it. Okay? So square root of half and root 2 over 2 are the same. Just one is a rationalized version of the other. Okay? So we come back here and we say, okay, for this one, my a came out to be root 2 over 2, and this a also came out to be root 2 over 2. So in other words, if I were to indicate that here, that is root 2 over 2, and this height is root 2 over 2. That means the coordinate here, right, for 45 degrees, this coordinate here is root 2 over 2, comma root 2 over 2. So we were able to find the coordinate of the point on the unit circle where 45 degree is marked as the central angle. Okay, so if you can think of this for other triangles, we can look at that, say, for 60 degrees here. Okay, so let me take the 60 degrees. It looks like this. So there's a 90-degree mark, and this is 60 degrees. If this is 90 degrees and this is 60 degrees, this must be 30 degrees, right? But if you actually understand the geometry behind this, this is actually half of an equilateral triangle, where an equilateral triangle has all three angles the same, and therefore all three sides are the same. So equilateral triangle. As the name says, equi means equal, lateral means sides. All sides are equal. That's because all the angles are equal. So their corresponding opposite sides are all the same. So in this case, what we have is that the angle opposite the 90 degrees, I'm sorry, the side opposite the 90 degrees, right, must be 1, right? This must be 1. And if you look at the sides, right, that is a side for the 60 degrees. So if you see the bigger picture of the equilateral triangle, if that side is 1, every side must be 1, right? 1 and 1. But if you look at just the right triangle here, maybe I'll try to kind of shade this. That was too dark. Sorry about that. But if you look at the shaded triangle alone, this side 1 is for the entire base, but we need it only for this. But we know that that's half of it. Therefore, this is a half, right? And so using that concept here, what we do is that we understand that it's half of an equilateral triangle. Therefore, the side 1 is half for just the pink shaded triangle, right? So we now use that concept and then try to see what the sides could be for a 60-degree angle. Okay. So in this case, if we were to go ahead and use the unit circle equation, squared equals 1, well, we see that the sides, right, will have to be twice. The side opposite 30 degrees must be half of the entire side. And so I have to make sure that I got that. And so we have, so what we see is if I were to, again, draw that triangle out here and keep it as C, the hypotenuse, right? So you know that all three sides should be C, okay? And now if I'm only worried about this triangle here, right? I mark it as 90 degrees. If I'm worried about this triangle, then let's say this was side A, this part would be B, right? Just this length would be B. But you know that this is an equilateral triangle that is bisected, right? This was 60 degrees. But this is bisected, and therefore this is just 30 degrees. So the opposite side is half of that 60-degree angle. And therefore, what you can see is this would be B and this would be B. In other words, C is 2 times B, right? And so if I were to use the Pythagorean theorem, c squared equals a squared plus b squared, I can see that the c squared is nothing but 2b, right? A squared plus b squared. We'll come back to the x because a and b is what we did for the other one too, and we can come back and indicate what a and b are. So we have, in this case, a as the vertical height, right? So we'll come back to that. That's going to be 4b squared equals a squared plus b squared. Now we need to solve for a and write it in terms of, we can write it in terms of b, right? And so your a squared is 4b squared minus b squared. A squared is 3b squared. So a is square root of 3b, assuming you're taking only the positive sides, right? Yeah. Now here comes the thing. If you are able to say what b is, you can find a, isn't it? So if my b is half, right, then a is root 3 over 2. You can kind of see that here, and that's what I wanted to show you here. So here we saw that the unit circle has the hypotenuse as 1. Okay, so C is 1. So if C is 1, B is half. So let me come back here. This implies if C is 1 unit circle, it implies C equals 2B, 1 equals 2B, which means B is half. Right? If C is 1, then B is half. So coming over here, if B is half, A is root 3 times half, which implies A is root 3 over 2. So collecting all these details, okay, I have A as root 3 over 2, B as half, and C as 1, right? And if you collect all of these together, what we get is that your A, right? Your A was this vertical height. So I'm going to correspond that to this height here. Okay. So this is your A, which was, let's come down here. A was root 3 over 2. Root 3 over 2. And this was your B, and B was a half. So if you come over here, the coordinate for this point is x comma y, so half comma root 3 over 2, right? And if you looked at the 30-degree angle here, right? That would be the flip of it because you're just doing the other way around. And so that would be √3/2 comma half, because the angles got flipped. So it's the same equilateral triangle argument that you'll place. Excuse me. You will just have the 30 degrees and the 60 degrees interposed, so that you now have the opposite side and the adjacent side switched. Okay, and that's getting a little cluttered here, but you can kind of see how we can build these coordinates. So to kind of put it in a more in a more tabular form, I can put it out like this, right? So we can say angle, sine, cosine, okay? I'm just trying to draw a table here. So now we have these special angles, and so I'd like to call 0 degrees or 0 radians, okay? So that could be 1. And then we saw 30 degrees, you know, the corresponding radian measure. You know how we did the conversion, right? 30 degrees times pi over 180 degrees. And so 30 degrees would convert to pi over 6 radians. So I don't have to write the word rad, so I'm just putting it as pi over 6. That's how we convert each one of them. And so we now have 45 degrees, which converts to pi over 4. It's a good idea to remember these conversions. And then you have 60 degrees that converts to pi over 3. And so with all these things, we now have for the unit circle. So remember that sine here, let me also quickly note that sine is actually your y and cosine is actually your x. So when you come back here to the circle and if you put the values that we detected earlier, you can see that x coordinate is the cosine and y coordinate is the sine. So for 0 degrees, sine would be 0 and cosine would be 1. Sine would be 0 and cosine would be 1. And then 30 degrees, come back there. It's √3/2.5, but this is your x and this is your y, meaning your cosine and then your sine. So half and √3/2. Likewise, if I fill the others, I would have it like this. And this is just for the, and then there's one more. I should have written the 90 degrees because we have those. Let me make more room here. $90 will be the last, special angle. And that will be pi over 2. And this we saw as 0, 1, so x, y. But in this case, my table is y and x, so I have it like this. So we got all those values in. And these are our popular angles. So as you can see, you have 1, 2, 3, 4, 5. 5 popular angles in quadrant 1. Okay. And we like to either use the tabular method or the unit circle method. We prefer the unit circle method because it's just a quicker view to have them all visible. So if you recall, this is the actual full unit circle that we would generate from it. Okay. So this unit circle is, if you looked at just the first quadrant, it gives you all those coordinates. Personally, I take issue with the representation here, that it should actually be parentheses because that's a correct representation of coordinates. I am not sure why this image has that, but I thought this was a colorful image that helps us to see these angles more visibly. So I chose this one, but I want to give this image with the disclaimer that your coordinates must be written properly. It's always parentheses x, y. All right, so we got that. And I will also go over how we can remember this on a unit circle. So we have derived it, but there is a way to remember writing the circle correctly, because henceforth you will be asked to call upon these angles within a problem. So you have to have your unit circle handy, and you will have to draw it by yourself from scratch. So we'll go over that as well. Okay. And then we have the other objective that we'll be looking at now. So the objective here is to figure out sine and cosine values with reference angles. Okay. So you have the angles, and the values are these coordinates. That's what we mean by values. So how do we find that? First of all, let's understand what reference angles mean. So by definition, reference angles, it refers to the measure of the smallest positive acute angle. Smallest, positive, and acute, formed by the terminal side and the horizontal axis. We always like to write this, okay, so that we have an idea of how we're measuring this angle. Okay. So there's the terminal side of the angle. Theta, in this case we're using theta or t, and the horizontal axis. You know that the horizontal axis is always the starting point for measuring your angles. So let's take a look at what it means. Smallest, we understand smallest. Positive, also we understand positive. Acute, not angles that are cute, okay, although they do look cute. These are angles that lie between 0 and 90 degrees. Okay, so these are angles that are small, positive, and they must lie. They must be an acute angle, so they should lie within the first quadrant technically. Okay? So naturally, your first quadrant itself is already measured in reference angles, right? But if you go to other quadrants, then they measure more than 90 degrees, and our job is to see if we can rewrite that angle using reference angles so that it becomes a small positive angle. Okay, so let's look at the ways in which we can obtain reference angles for angles that lie outside or past 90 degrees. So if you had a setup like this, where you have unit circle drawn on your XY axis, you have the quadrants, numbered this way, right? You always start in the top right quadrant, the top right corner as your first quadrant, and you go anti-clockwise to counter. So you really have to be very careful, because if you went clockwise direction, we would be looking at different quadrants. Even though you might be thinking the correct quadrant, you may be referring to the wrong number. So please watch out for that. That this is how it is measured or numbered. So if your angle, okay, your angle of interest theta, lies in the first quadrant, it's already your reference angle. Okay, and the way we represent reference angle is using theta prime. Okay, theta prime is your reference angle. That little dash there is called the prime. Okay. So this is your reference angle, and in this case, the reference angle for theta is theta prime itself. Theta prime is theta itself. Okay. Now, if your reference angle, and if your angle lies in the second quadrant, let's say, it's shaky.
I can learn to understand you much better if I can get familiar.
Sorry about that. All because I was trying to draw something. Okay, so now this is your angle theta. Okay, now notice that, to go back to the definition, the measure of the reference angle is a measure of the smallest positive acute angle. Now this angle is measured positive. I'm not sure why I can't really put my hand there. I put my hand on the screen. It's bringing all other functions alive. All right, I think that's better. So it says smallest positive angle. So this angle is measured like this. And this angle is going over 90 degrees, right? So it is still positive, but it's not small or it's not acute, because it's not acute, therefore it's not small. So what will be my theta prime? Well, theta prime says, well, if you are more than 90 degrees but less than 180 degrees, right? This is 180 degrees and this is 90 degrees. If you're more than 90 but less than 180 degrees, then you want to do 180 degrees minus your angle theta to get your theta prime. Okay? Or if you are using radians, it would be pi over, I'm sorry, 180 degrees is pi. Pi minus theta. Theta prime would be pi minus theta. So let's say it was 120 degrees. If theta was 120 degrees, to find its reference angle, the reference angle would be 180 degrees minus the 120 degrees, which is 60 degrees. So theta prime would be 60 degrees. Okay. Then we have third quadrant. Let's say your angle was now in the third quadrant, okay, somewhere here. I'll make it thick so we can kind of see it. Say that was my angle theta. Now that angle theta is still positive, but it's going all the way around, and it's definitely not small and therefore not acute. So you have this angle that is exceeding 180 degrees, right? So if it's exceeding 180 degrees, what do we do? Well, it is exceeding 180 degrees, but it is less than 270 degrees. And so for that, what we do is, because your angle is bigger than 180 degrees, subtract that angle from 180 degrees, okay? Or if you're doing it in radians, it's going to be theta minus pi, theta prime, right? So if you had a larger angle, an angle more than 180, say you had theta is 200 degrees. If theta is 200 degrees, its reference angle would be 200 degrees minus the 180 degrees, which would be 20 degrees. 20 degrees is an acute angle because it's between 0 and 90 degrees, and you found a corresponding reference angle. Okay. So what we have here is, what if your angle was in the fourth quadrant? Again, remember, this is a positive angle that's going all the way around. That's my theta. Okay. So my theta is, that's my 360 degrees, right? It's 0, but then it went all the way around. It didn't cross 360 degrees, but it is more than 270 degrees, but less than 360 degrees. Then what we do is we use the reference angle, which is going to be 360 degrees minus your angle theta, right? Because it's less than 360, so you do 360 minus theta. And again, if it is radians, remember 360 is 2 pi, so theta prime would be 2 pi minus theta. Okay. So what I'm trying to kind of show you is, these would be the corresponding theta prime angles. So for the first quadrant, theta itself is theta prime. They are the same angles. But for the second one, we're trying to see what this will be. This will be theta prime, right? 180 degrees minus theta. Oops. Uh-oh. Something crashed. All right, I'm going to kind of pause the video here and see what's going on. All right. So now we have this angle to be theta prime, because theta prime is an acute angle and it's coming from the horizontal axis, right? So from the x-axis, you are measuring a corresponding theta prime. If you come over here for the third quadrant, this is coming back as theta prime, because that is also measured from the corresponding x-axis, right? But from the negative side, x-axis. But then it's creating an acute angle with the angle theta. And then lastly, we're looking at this as the theta prime, because that is your x-axis forming an angle with the theta on the other side of the terminal side by creating another acute angle. So please remember that these are your reference angles, all right? So then with that in mind, we will now look at, we'll just take a look at one of the problems just to give us an idea. So find the reference angle . of 225 degrees. Okay, 225 degrees. So our job is to see which quadrant this lies in. Okay? If you go back, you can see that this is lying in the third quadrant because it's more than 180, but less than 270 degrees. And if it's in the third quadrant, because it exceeds 180 degrees, this angle, you will subtract 180 degrees from this angle. Okay? So this implies reference angle is 225 degrees minus 180 degrees. You always want to do 180 degrees minus this, but remember it has to be a positive angle, the smallest positive acute angle. So sometimes the book will also give it to you like this. It will give you absolute value of 180 degrees minus 225 degrees. Okay? So they will give out the same answer. Now 225 minus 180 is 45 degrees. You're getting the positive angle and it's acute, and that's your reference angle. But if you did this in the absolute value version, you would get negative 45 degrees, but that's in the absolute value, so it returns a positive angle as 45 degrees. So that is how we kind of understand the reference angle. So the reference angle of 225 degrees is 45 degrees. You will know you got the correct reference angle. Of course, you should do the calculations, right? But some common sense check would be, is it a small angle? Is it positive? Is it acute? And it's all of them. So we found the reference angle. Okay. And what happens if you were to use this in a real life example? So here's the question. A whole pizza is 360 degrees. If the reference angle is 120, or reference angle of 120 degrees is used as a guide to cut the pizza, how many slices of pizza will there be? So quickly draw the graph, and thankfully, the pizza is in the circular shape, so you can kind of see that you want to slice this. You want to know how many slices there will be if you're using 120 degrees as the reference angle. Okay. So if this is 120 degrees, it's going to be like this, right? Oh my gosh. Everything went off. Okay. That will be 120 degrees, right? So the reference angle for this would be this angle here, right? What will this angle be? And that is where you go back to this chart and see where 120 degrees is. It's in the second quadrant. So use the relation we saw in the second quadrant, which is 180 degrees minus 80. So 180 degrees minus theta, I said 80. So 180 degrees minus theta. In this case, theta is 120 degrees. So theta prime, or the reference angle, is 180 minus 120, which is 60 degrees. Okay. And so we come back here and we say, well, we have the reference angle to be 60 degrees. So that is how you're going to slice your pizza. So there are 360, the entire pizza is 360 degrees, right? The whole pizza. So if you were to divide this by 60 degree marks, do 360 over 60, and that gives you 60 degrees, right? Or I mean 6, that gives you 6. So that means there will be 6 slices of pizza. You cut the pizza into 6 equal slices because you measured the reference angle of 120 degrees to be 60 degrees. And so each pizza slice will be 60 degrees. Yeah. And so that's kind of an application. Let's take a look at radians. Okay. Find the reference angle of negative pi over 4. Very clearly, this immediately looks like a small angle because you look at the pi over 4, you know in your head it's 45 degrees, but it's a negative angle. And remember, reference angles must be positive, small, positive, and acute. So because of that, we now have the question of converting this negative angle into a positive angle. So we want it to be positive, right? So first, let's mark this angle. This angle would be, you can draw the circle if you want. Also, just draw the angle if you wanted. Anyway, so we have negative 45 degrees to be here, negative pi over 4. Because if you were to measure this in the in the positive, in the negative direction, that would be negative pi over 4, right? But then we want to make it into a positive angle. So it's lying in the fourth quadrant, right? Because it's lying in the fourth quadrant. Let's come back here. Fourth quadrant would be 360 minus theta, 360 degrees minus theta, but here it's in radians. So it is going to be 2 pi minus theta, okay? Now, if you were to use it as it is, right? So that will be 2 pi minus theta. For us, theta itself is negative, so negative pi over 4. If you did this, if you directly did this, what happens is you get 2 pi plus pi over 4. In this case, you're exceeding 360 degrees, right? So this would exceed 2 pi or 360 degrees. We want it to be acute. You want it to be within 90 degrees. So if you look at this negative measurement of the angle, the negative measurement actually is the reference angle. But if you measure the angle from the x-axis to its terminal side, the negative pi over 4 measures the same as pi over 4, right? So this implies the reference angle of negative pi over 4 is itself pi over 4, right? Because the fourth quadrant with a negative measure is the same as the first quadrant with a positive measure, right? And so because of this unique circumstance, it looks like we got the same answer, but just changed the sign. We didn't just simply change the sign. We considered what change this would bring if you were to apply the formula directly, and we saw that that wouldn't really help. And so we just understood the concept of reference angle by taking the measure of the smallest positive acute angle from the horizontal axis to the terminal side. Let's quickly talk about even and odd trigonometric functions. So even and odd. Trig functions. We've seen this in algebra, okay, even and odd functions. So let me quickly give you an overview in algebra. If a function is even, okay, it implied, let me write function. Even function implied that it was symmetric about the y-axis. Okay, think of a butterfly. Okay, symmetry about the y-axis. And algebraically, this is how we showed. We said, if you switched your x's to negative x, it did not change your function. Okay, and for odd functions, it was symmetry about the origin. Think of odd and origin, OO. That's your way to remember this. What we say is, well, if you, see, I can't talk and write. Let me write it first. If you had your x is replaced by a negative x, then that result would be the negative of your function, right? For even function, if you changed your x to a negative x, no change to the function. Here, you change x to a negative x, your function is multiplied by a negative. So you get the negative of the function. That was an algebra. Here in trig, what we're saying is, we have to go look at each function because we have 6 trigonometric functions and see if they're even and odd. So to make it easy, we have cosine to be an even function, okay, which means cosine of theta, I'm just putting it in parentheses just so you can see that, is the same as if you had the theta replaced by a negative. So if you replace your theta, the angle, with a negative angle, your cosine absorbs it and makes no change to the function. Okay, the negative is absorbed. Because cosine, it works for cosine, its cousin is secant, right? Remember, secant is the flip of the cosine function. Secant is the reciprocal of the cosine function, so it works for secant as well. So secant also is even because it absorbs the negative sign. Okay. And for odd functions, the other 4 are all odd functions. So let's start with sine. Sine, I'll just say negative theta, is the same as negative sine theta. As you can see, when you replace the theta with a negative theta, it did not absorb that minus, but it kind of, what do I say, it's like spitting it out, right? It's throwing it in front. So it could not absorb it, so it is rejecting it, and it's the minus is there in front of the function, not with the angle. This is helpful to convert all the negative angles into positive angles, and depending on the even or the oddness, the minus is either absorbed or the minus is thrown in the front of the function. We have sine, then we have its cousin, cosecant, also will behave the same way. So that negative is brought out. We have a negative cosecant theta. And then we have tan. Tan negative theta is negative tan theta. And its cousin, cotangent. So cot negative theta is negative cot theta. All right. So this is something we're going to use, especially when we do reference angles. It's going to come in really handy to move your angles, to convert your negative angles into positive angles. First of all, your reference angles by definition itself will give you positive angles, but it also kind of reiterates the evenness and the oddness when you have to switch from the negative angle to positive angle. So here we go. Use reference angles to find the exact value of sine 330 degrees. Okay. For this, draw your, now previously we just looked at the angle, now we're given the function, okay? 330 is in the fourth quadrant. So the reference angle for this would be, it should be this angle here, right? So on the graph, it must be this angle. So the reference angle is going to be 360 degrees minus 330 degrees, which is 30 degrees, okay? So now we have sine 330 degrees, okay, is now rewritten as sine 330 degrees, its reference angle is 30 degrees. However, remember that this is in the fourth quadrant, quadrant 4, right? So you have to make sure that you are looking at your sine 30 degrees in the fourth quadrant. So it is as if you had a negative 30 degrees, right? So to rewrite this in the fourth quadrant, it's as if you had sine with a negative 30 degrees. Remember, reference angles are always positive, but I'm trying to adjust it for the fourth quadrant because it's no longer just an angle, it's an angle with the function associated with it. So to find sine 330 degrees, I have to make sure that I'm getting the sign right. So sine negative 30 degrees would make this be a position in the fourth quadrant, right? But we know from the reference, from the even odd functions that sine, look at this one, sine is an odd function. So if I had a negative theta, it brings out the negative. So that means this negative is brought out as sine 30 degrees. Then you can go to your table or your unit circle to figure out that sine 30 degrees would be, let's go to that table. So sine and the 30 degrees is half, right? So that's half, but remember there was a minus in front of this. So that's going to be a minus half. So the value for sine 330 degrees using reference angles is this. And they said find the exact value. So please leave it as a fraction, as a simplified fraction. And that is the answer. What about this? Use reference angles to find the exact value of cosine 3 pi over 4. Okay, with the radians, it's a little difficult to see where this will be. Okay, but if you looked at your angles, in terms of radians, okay, this will be 0, pi over 2, pi, 3 pi over 2, and back to 2 pi. Okay? And so that kind of helps you to see where this might be. Okay, so 3 pi over 4 is technically half of 3 pi over 2. Okay, and so this must be lying in the third quadrant. Three pi over 4. And we need to find the cosine value for that, the coordinate, the x coordinate for this point on the orange circle, right? Now, if you are, we'll talk about conversion. We've spoken about conversion of radians to degrees. So that's another way for you to recognize which quadrant this will be. And so 3 pi over 4, let me show that here, 3 pi over 4 times 180 degrees over pi, right? That's the conversion. So do the conversion, and that will help you find the corresponding degrees, and that can also help you to see which quadrant this is in. But it's a good idea for you to develop the habit of understanding this in the radian format itself. Okay. All right, so this is in the third quadrant, is in quadrant 3. Okay, so reference angle for reference angles in quadrant 3. Let's go to that chart. For quadrant 3, the reference angle says do theta minus pi, okay, because it's more than 180 degrees. So theta minus pi. It always has to be from the horizontal axis. So it's either pi minus theta or pi plus theta, or if you go to the other side of the x-axis, it is directly the first quadrant angle, or it is 2 pi minus the angle, because that is the full circle landing back in the horizontal axis. Okay, coming back here, this was theta minus pi, right? So your theta is 3 pi over 4 minus pi. Okay. We now have, I don't know why the audio is just paused. I hope my volume is back up. Okay. All right, so 3 pi, wait a minute, 3 pi, oh my gosh, I copied the question wrong. I apologize. It's 5 pi over 4. How can 3 pi over 4 is actually in the second quadrant. Sorry about that, 5 pi over 4. 5 pi over 4. Well, if it was 3 pi over 4, we would have done pi minus theta, 5 pi over 4. All right, so that's 5 pi minus 4 pi over 4, right? If you took the LCD, which comes out as pi over 4, okay? So we are looking at this angle here, which is pi over 4. All right, so you are looking at cosine 5 pi over 4, which is in the third quadrant, okay? So if this is in the third quadrant, its corresponding reference angle, we just found that to be pi over 4, right? So this must be in the third quadrant. So this one must also give an answer in the third quadrant. In the third quadrant, okay, let me again write that out here. So this is first, this is second, and this is third, fourth. In the first quadrant, your x is positive and your y is positive, right? In the second quadrant, your x is negative and your y is positive, x comma y. The third quadrant, x is negative, y is negative. The fourth quadrant, x is positive and y is negative. Now we know that x represents cosine theta, and y represents the sine component, right? Sine theta. So in the third quadrant, your cosine and your sine both are negative. In particular, we're interested in cosine. So your cosine is negative. So you want to bring a negative to your answer for cosine pi over 4. Okay. So this negative is crucial because you are now adjusting it to the third quadrant. And then go ahead and use your table, and the table gives you negative root 2 over 2. And that's the exact value for cosine root 2 over 2. Okay. Now we have to look at how to remember to draw the unit circle correctly. Okay, so likely to draw unit circle like this, a plane graph. You have the x and the y axes, right? So let me mark those for you. So this is your x and your y, and this was your negative x, right? Negative y, got that. And then you want to draw the 45-degree mark here, right? The other orange one. So that would be your 45-degree mark. Okay. Just write that here. 45 degrees. Okay. So that's 45 degrees. That's 45 here. I'll come back and change the values, but just for you to see that it's 45 degrees here, here, and here, right? And then you want to draw the other one, which is like the 30-degree mark, the 30 and the 60. Likewise, this would have been the 30, the brown ones. The brown spokes are the 30 and the 60. Right? I measure 30 from the x-axis, right? So x-axis, up and down, 30. This is a 60 degree. And this again is your 30. I'm sorry, this was your 30. And this was your 60 degrees because you're using x-axis as a reference. I'm going to go back and change all these angles because, you know, they're in different quadrants. In each quadrant, this is how they measure, right? And then, of course, you have the 90, 0, and all that. So let's mark that. So this is 0 degrees, 90 degrees. The negative x-axis is 180 degrees. This is 270 degrees, and back to 360 degrees, right? Okay, so we got this. Now let's focus on the first quadrant, and then we will come to the others. So for now, I'm going to kind of clear all the other angles we wrote. Because with the degrees, you're kind of fine, but I want to use the radians to help us with this. So I just want to do the degrees for the first quadrant, and then we'll begin to generate the radians, okay? So for your first quadrant, if you go back to the table, right, we found that these coordinates, I'm just wondering what color to use. Okay. This coordinate here was 1, 0. Right? Oops, I'm looking at the wrong one. I should look at the x-axis, sorry about that. That's 1, 0 for the x-axis. Then, if you recall, 45 degrees was root 2 over 2, comma, root 2 over 2. And this was half, comma, root 3 over 2. And this was root 3 over 2, comma, half. I'm sorry, it's really, really small. I'm trying to accommodate all of these here. And this was 0, 1. You remember this came from our derivation and from the unit circle, the table that we wrote based on this, okay? And we also found that our angles in radians, this was 0 itself with no degree symbol. And 45 degrees was pi over 4. 30 degrees, again, do the conversion, right? 30 degrees would be pi over 6. This thing just disappeared, so that would be 60 degrees. The 60 degrees was pi over 3. Okay. And 90 degrees was pi over 2. We got all the degrees, all the angles in radians. So this is your first quadrant. We kind of filled the first quadrant. How do we fill the other quadrants? So for that, first I want you to see how to fill in your radians first, right? What happens? What does a radian measure for the second quadrant here, here, here? So let's take care of that first. Before that, I would like to draw your attention to my green markings, okay? So I want you to pay attention to just this spoke, the 45-degree mark. Just look at the green, okay? All the tick marks that I make for the green. I'd like you to count that. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 tick marks. In other words, your circle is divided into 8 parts, okay? So the entire revolution is 360 degrees or 2 pi, and we're dividing that 2 pi into these 8 parts, right? So you're dividing 2 pi into 8 parts. So 2 pi over 8 is pi over 4. So each part is a quarter, right? Pi over 4. So I'm going to use green for this again, so you can see that 2 pi. So this will be pi, and this will be pi over 4, okay? So that's your starting point. First quarter is pi over 4. Then go to the 90-degree mark, the next green check mark. That will be 2 pi over 4. The third check mark is 3 pi over 4. Fourth one is
I can learn to
4.
understand you.
How do I get rid of that? 4 pi over 4. And this would be 5 pi over 4. The next tick mark is 6 pi over 4. 7 pi over 4. And the 8th quarter comes back here as this check mark here, 8 pi over 4. You with me on this? Because you started with the first quadrant. You started here. This was your first point. That was your starting point. So you started from the first quarter and came all the way back to the 360-degree mark. Yeah? And if you go back and if you reduce the 2 pi over 4, that gives you pi over 2, which is what we got here. 3 pi over 4 cannot be reduced, but 4 pi over 4 comes back as pi, which is your 180 degrees. 5 pi over 4 cannot be reduced. 3 pi over 4 reduces to, 6 pi over 4 reduces to 3 pi over 2, which is your 270 degrees. 7 pi over 4 cannot be reduced. 8 pi over 4 reduces to 2 pi, which is what we have. We come back to the 360-degree mark. So that helps you to generate the radian measure for all your spokes there, okay? Next, I'd like you to pay attention to the red tick marks, okay? So 0 is the starting point, but after that, the first starting point, meaning would be the first 30-degree mark. So look at the red check marks, okay? 1, 2, 3. You're skipping the 45-degree mark. You're not skipping the axes, but you're skipping the 45-degree mark, okay? So 1, 2, 3, skip this. And then go here, 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 skip the 45-degree mark, here, 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 skip 45-degree mark, here, and back here, okay? All right, so this is pi over 6 is your first mark, right? You see this, pi over 6, 30-degree mark. So this is pi over 6. The next mark would be 2 pi over 6. This third one is your 90-degree mark. That would be 3 pi over 6, 4 pi over 6. Skip this. Go to every red mark that you have. 5 pi over 6, 6 pi over 6, 7 pi over 6. Skip this. 8 pi over 6, 9 pi over 6, 10 pi over 6. Skip this. 11 pi over 6. Let me write that again. 11 pi over 6. And then back here to 12 pi over 6. You know that you did it right because you come back here at 12 pi over 6, you know that reduces to 2 pi. Now go back and reduce all the ones you know. 2 pi over 6 reduces to pi over 3. 3 pi over 6 reduces to pi over 2. 4 pi over 6 reduces to 2 pi over 3. 5 pi over 6 does not reduce. 6 pi over 6 reduces to pi. 7 pi over 6 does not reduce. 8 pi over 6 reduces to 4 pi over 3. 9 pi over 6 reduces to 3 pi over 2. 10 pi over 6 reduces to 5 pi over 3. 11 pi over 6 does not reduce. 12 pi over 6 reduces to 2 pi. So that is how you generate the angles for in radians for the other quadrants. I know it looks cluttered, but once you get the idea, you will be able to fix their positions appropriately. Okay. And lastly, I want to fill the coordinates for all the other points as well. Okay. Now, the easy points would be the 90-degree marks, right? So we had 0, 1 here, 1, 0, 0, 1. This will be negative 1, comma 0. And this last one would be 0, negative 1. So those ones, those 4 points, we got them. How about the others? So then we come back here and see how they match. Now remember, if you come back to this one, right, I said positive, positive, negative, positive, negative, negative, and positive, negative. So your coordinates will have to carry that sign. So x coordinate must be negative, y coordinate must be positive in your second quadrant. So come back here. And here, on the other side, I have half and root 3 over 2. The corresponding side, this side, the coordinate will be negative half and root 3 over 2 because your x coordinates must be negative. That doesn't look right. Negative and a half. Yeah, that's better. And this is root 2 over 2, root 2 over 2 on the other side. So it should be root 2 over 2, comma, root 2 over 2 as well. Okay. So negative. So this was root 2 over 2, root 2 over 2, but with the x negative, it will be negative root 2 over 2 to root 2 over 2. And then this one, on the other side, corresponding rate is root 3 over 2, comma half. So this will correspond as negative root 3 over 2, comma half. We'll do the same thing here, but in this point, I mean in this quadrant, both your points will be negative, right? So this would be, this is 30 degrees off down here. That's going to be negative root 3 over 2, comma negative half. Both will be negative. 45-degree mark is kind of easy because both x and the y coordinates carry the same value. And this one would be negative half and negative root 3 over 2. And in the fourth quadrant, your x is positive and your y is negative. So this is going to be positive half with a negative root 3 over 2. This is going to be positive root 2 over 2 with a negative root 2 over 2 for the y. And this would be, lastly, positive root 3 over 2 with a negative half. All right. Now YouTube also gives you other quick ways to remember, but this is the mathematical way to remember, but you have other quick clues as to remember your coordinates, okay? So just as a last piece here, I'd like to give you that quick clue. So if you had this 45 and the 360-degree mark. Okay. So for that, what we're saying is, okay, if you're looking at the coordinates here, you know that this one would be pi over 6, pi over 4, pi over 3. Right? The coordinates would be, well, this is a trick. This is not a derivation. This is a trick. You know, this is how your coordinates will be, right? The trick says, well, drop a 2 over 2 for each one of them because they all have the over 2. And then it says do 1, 2, 3, and then 1, 2, 3 back. Okay, in reverse for the other one. 1, 2, 3, and then 1, 2, 3. Then it says take the square root for all the numerators. But square root of 1 is 1, so this is same as half, comma root 3 over 2. This will be, of course, root 2 over 2 and root 2 over 2. And this would be root 3 over 2, but that will become a half. So this is a quick trick to remember the coordinates. So I think that's a handy trick, but do not replace tricks for original concepts, which I have explained above here. But the trick is definitely helpful to quickly, draw your unit circle and not make an error. Okay, so I hope that is helpful. And with one last piece here, I remember we said plus plus, minus plus, minus minus, and plus minus for the first. So I'll just write the quadrant numbers too. So what we understand here is that in terms of trig functions, we have a quick way to remember this: ASTC. Okay, ASTC, because I'm going in the order of the quadrants: 1, 2, 3, 4. 1, 2, 3, 4. And this is the way I would remember all silver teacups. At least this is how I remember from school when I studied. But I think now they use another way to remember this. Mnemonic is, what is it? All students take calculus. That's one way to remember. Okay? And you can build your own, whatever, right? But what it really means is A stands for all trig functions. This is for trig functions. So all trig functions are positive in the first quadrant. Okay? In the second quadrant, all sine functions are positive. When I say sine functions, I mean its cousin as well, right? Which is cosecant. And in the third quadrant, all tan functions are positive, because tan is sine over cosine. So negative over negative is positive. And then in the fourth quadrant, cosine is positive, because your cosine is the x-coordinate, and therefore the x-coordinate is positive, right? So this is for your trig function, this way to remember. And as always, remember that your x, comma y is always your cosine theta, comma sine theta. It's not sine, comma cosine. It's cosine, comma sine. So please remember that whenever we do the plus or the minus, it's both for x and the y, but also in the background for trig functions, it's the sign of the trig function. Is the trig function positive or negative? And this table helps you to capture that. So I hope you enjoyed this video. We had a few hiccups, but we managed through it. And I will see you in the next video.